Okay, so welcome to this tutorial video. In this video, we're basically going to discuss a problem that I designed myself for a tutorial question assessment for some level 4 undergraduate engineering students. So the problem goes like this. It's a mass balance problem. So it goes aqueous ethanol is purified by undergoing a double distillation process. The feed stream enters the first distillation column at 100 kilos an hour, containing 40% ethanol by mass. The distillate and bottom streams of the first column contain 90% and 10% of ethanol by mass respectively. That distillate stream enters the second distillation column with distillate and bottom streams of 99% and 1% ethanol by mass respectively. Then you're asked, draw a mass flow block diagram of the system and show appropriate units, mass flow rates and mass compositions. Then you're asked to determine the mass flow rate of the distillate stream, leaving the second column, and then finally you're asked to determine the percentage proportion of ethanol in the feed stream that leaves in the distillate stream of the second column. Okay, so evidently there's quite a lot to unpack here, right? It's quite a wordy question, and I made it wordy for a reason, just so it gives students an opportunity to kind of translate and dissect what it's saying. So aqueous ethanol. Oh crap. Let's go back there. Aqueous ethanol. So immediately, some students might know what this means. Aqueous just means dissolved in water. Let's call it H2O. And ethanol is an alcohol with 2 carbons in it. I mean, I don't know how useful that is, but ethanol kind of looks like this. This is what an ethanol molecule looks like if you've never done chemistry. So it's basically this molecule and this molecule, water, right? Aqueous ethanol, it's just a mixture. You could say it's a mixture of ethanol and water. Is purified. Okay, well, you'd assume that the thing being purified is either the water or the ethanol. Just by intuition, it makes sense that we're talking about purifying ethanol here, right? So this aqueous ethanol contains 40% ethanol, and by purifying it, we're essentially separating that ethanol from the water, so we're purifying it. Okay. Undergoes a double distillation process. Okay, so by double distillation process, we basically just mean that it gets distilled and it gets distilled again, right? The feed stream enters the first distillation column at 100 kilos an hour, so we can say that the feed, because that's, yeah, I mean, it literally says it there, the feed stream is 100 kilos an hour, contains 40% ethanol by mass. The distillate and bottom streams of the first column contain 90% and 10% ethanol by mass, respectively. Okay, the word respectively here, the way we take the word respectively, if you're unfamiliar, this sentence says the distillate and bottom streams of the first column contain 90% and 10% ethanol by mass respectively. That basically means that the distillate contains 90%. I mean, let me be crystal clear. So the distillate contains 90% and the bottoms contains 10%. That's what we mean by respectively, basically. So if you're unfamiliar with that, that's what that means. The distillate stream enters a second column with distillate and bottom streams of 99% and 1% ethanol by mass, respectively. So again, it's the same deal with this word, respectively, if you've never encountered it before. Distillate, 99%. bottoms 1%. So let's kind of take this. That's not what I was looking for. Let's take this. Oh, shame I don't know how to use a keyboard. Oh, you know what? Don't need to do that at all. Let's just do some zooming out. Let's try and understand this then in the context of a mass flow block diagram. So the first column has a feed of 100 kilos an hour. So remember we show streams using arrows. It might be conventional to write the mass flow rate up here and the mass compositions down here. So we'd say, let's call it XC2H 50H. That's just what ethanol is. You could just write ethanol there, right? Equals 0.4 and XH2O equals 0.6. So this enters a distillate stream, a distillation column, sorry, right? And a distillation column has two exit streams typically. The distillate stream, which you typically draw at the top, and the bottom stream, which you typically draw at the bottom. And we can see that in this second sentence here, the feed stream enters the first distillation column at 100 kilos an hour. We've already got that. Okay. The second sentence says the distillate streams and bottom streams with the first column. Let's call this first distillation column. The distillate and bottom streams of the first column contain 90% and 10% ethanol by mass respectively. So we don't know the mass flow rate of the distillate and bottom streams, so let's just label them. Let's call that M2 and call that M3. And we know that in the distillate column, in the distillate stream, sorry, we've got 90% ethanol, 90% ethanol. Hang on, sorry. Let's just do this again. And it makes sense that the rest would be water, so that would be 10%. Okay, I'm running out of room here, but oh well. And then the bottom stream contains 10% ethanol, so we could say XC2H50H equals 0.1, and the XH2O equals 0.9, right? And there's this second distillation column here. Let's zoom out. Draw our distillate stream and our bottom stream. And let's look back at the question. The distillate stream enters a second distillation column, which is just M2 here, with distillate and bottom streams of 99% and 1% ethanol by mass respectively. So again, we're not given the mass flows of the distillate and bottom streams. So okay, let's just label them then. M4, M5, and let's draw these mass compositions. So X C2H50H equals 0.99 because it says 99% is ethanol in the distillate stream of the second column, and then that will be 1%. And then down here, what does it say? 1% ethanol by mass respectively in the bottom stream, so we'd say XC2H50H equals 0.01, and then that must mean that the water is 99%. Okay. Would that get full marks? Yes, it would get full marks just by looking at it. The reason it would get full marks, this is a very crude way of going through things, but the mass flows are given. The streams are all shown in the correct configuration. The units are labeled, and the mass compositions are shown as well. So that would get full marks. Part B then is to determine the total mass flow rate of the distillate stream leaving the second column. So what we're trying to find here, the total mass flow rate of the distillate stream leaving the second column. So the second column is this column, and the distillate stream is this stream here. So what we're trying to find then is M4. Okay. Now, in order to find M4, we can carry out a mass balance. And how might we start a mass balance? Well, we might start by doing a degrees of freedom analysis. So I'm going to move the screen. I'm going to move the question off the board if that's okay. Oh, crap. Right. So there are 3 different degrees of freedom analysis that we can carry out here. The first one is a degrees of freedom analysis of our first column. Okay. Let me see if I can show this. So we can carry out a degrees of freedom analysis of our first column, and we can kind of imagine when we do this, we're kind of drawing bounds around our first column. We're basically imagining only the things that are going in and out of our first column. Okay, so that means everything else is disregarded. That means the M4, well, M4 doesn't, we're unconcerned with that. M5, we're unconcerned with that, right? But the feed stream, M2 and M3, we are concerned with because these are streams that are either entering or leaving the first column. So for our degrees of freedom analysis, that might look like this. Let's just write DOF here first, col. So if you remember degrees of freedom, we take the number of unknowns. Let's write this out actually. Degrees of freedom equals number of unknowns minus number of independent balances. Minus other relations. This is stuff that we've covered before, so I don't want to kind of repeat myself here. If you'd like to go over degrees of freedom analysis again, there is material on Canvas that you can access, or you can just visit the Ask and ask me. Okay, so let's have a look at our first column. Let's zoom out again. Goodness me. Right, so how many unknowns do we have? 2, right? M2 and M3. So in this case, 2. How many independent balances do we have? Well, we can do an independent balance for our ethanol. We can do an independent balance for our water, and that's about it. So we have 2 independent balances. Other relations, we don't have any. But clearly, when we do a degrees of freedom analysis of our first column, we have 0 degrees of freedom. Okay, just for the sake of doing it, and I'll do this real quick, I'll do a degrees of freedom analysis on I'll do the other degrees of freedom analysis that we can carry out. So we can carry out one on our second column here, so we only consider things that come in and out of our second column. That is M2, M4, and M5. Those are our unknowns for our second distillation column, so that's 3 unknowns. Minus, again, 2 balances, so we would have 1 degree of freedom for our second column. And then we have a third degree of freedom analysis that we can carry out, which is our overall degrees of freedom. So that's basically when we consider what's going in and out of our whole system? That boundary would cross M3, wouldn't it? This is getting messy now, sorry. So what's going in and out of our whole system? The only one we disregard here is M2, right? Because M2 is kind of inside our system. So the unknowns that we have here are M3, that's leaving our system, M4 and M5. Okay, so we have 3 unknowns there. Oops. 3 unknowns there, and then again we have 2 independent balances, 1 for ethanol, 1 for water, and that leaves us one degree of freedom. So it's clear then, based on this degree of freedom analysis, that we need to do a balance or balances for our first column because it has 0 degrees of freedom, and we understand that 0 degrees of freedom indicates to us that this is a solvable, that carrying out balances on our first unit is a solvable problem, right? So, okay, if we want to carry out a balance, we would consider, for the purposes of what has been covered in this module, mass balances obviously can get much more complicated than this, but for the purposes of this module, we can say that mass balance is given by this general idea that what goes in is equal to what comes out, right? There's nothing generated, there's nothing consumed, there's nothing accumulated, so we can just say in equals out. So what's going in? Well, for ethanol, we can say we've got 40 kilograms, right? That's 40% of our 100 kilograms an hour. And then what's coming out? This is for our first distillation column, remember? So what's coming out? Well, that is 90% of our M2 stream and 10% of our M3 stream. Now, is this equation, that M looks awful? It still looks awful, but slightly better. So is this equation on its own solvable? Well, no. The reason it's not solvable on its own is because we've got 2 unknowns, right? If we had just 1 unknown, then yes, it would be solvable, but we have 2, so it's not solvable. Okay, let's move on then. Let's do a mass balance for our water. So we've got 60 kilos per hour entering our first distillation column. Leaving our distillation column, we've got 10% of M2 and 90% of M3. Okay. So this is these are our mass balances. Now, by inspection, what does this look like? Well, it just looks like a simple simultaneous equations problem, right? If you remember, there's 2 common methods for solving simultaneous equations. You might use elimination, or you might use substitution, or you could use a graphical method. I'm going to choose to use the elimination method here, just because it's what my intuition says. You could use substitution here, but it might be a bit more lengthy in carrying out. So the idea behind elimination is that I'm trying to eliminate one of my unknowns. So it might make sense then to multiply one of these equations. Let's label these equations actually. Let's call that equation 1 and that equation 2. I would want to multiply one of these equations so that one of the coefficients of the unknowns becomes equal to one of the coefficients of the other unknowns. So then when I subtract or add this new equation from that equation, it eliminates one of the unknowns. I might have explained that poorly there, but let's kind of see this idea in action. So what I'm going to do is I'm going to multiply this second equation by 9. The reason I'm going to multiply it by 9 is so that this 0.1 M2 becomes 0.9 M2, which is obviously equal to this 0.9 M2 in this first equation here. So I'm going to say my second equation times 9 gives me, well, 60 times 9, that's 540. And as we've just discussed, 0.1 m2 times 9 gives 0.9 m2. And when I multiply my 0.9 m3 by 9, it gives me 8.1 m3. Okay. Now, I'm going to subtract my first equation. So subtract my first equation from that, and let's see what happens, right? So I'd subtract this 40 from this 540. That gives me 500. I'd subtract this 0.9 m2 from this 0.9 m2. That obviously gives me nothing, right? That's where the elimination comes in. 0.9 m2 minus 0.9 m2 gives nothing. And then I would subtract this 0.1 m3 from this 8.1 m3, and that would give me 500 equals 8 m3. Okay. Is that solvable? Yes. I just need to divide both sides by 8, right? So I can say m3 is equal to 500 divided by 8, which is equal to 62.5 when I type it into my calculator. Now, I could do the same process for my M2. However, when I go back to my mass flow block diagram, what I could effectively do now is rub out this. Oh dear, that's created a bit of a problem. I could rub out that M3 that I had there originally and replace it with my 62.5 that I've just obtained. And if 100 kilos an hour is going in, and 62.5 kilos an hour is leaving this bottom stream here, then can you see how this M2, this distillate flow here, would be equal to 37.5, just because that's 100 minus 62.5. So I'm just going to go ahead, I'm going to rub out M2 there. Oh, I need to get better with this, don't I? 37.5 kilograms per right. So now that we've solved that, note now that if I did my degrees of freedom analysis again, I could scratch off my three unknowns and replace it with 2 now, right? Because one of the unknowns was M2, this here, but I've now found its value, so it's no longer unknown, and I would effectively have 0 degrees of freedom for my second column. So let's carry out a mass balance for my second column then. Again, in equals out. So in terms of my ethanol, that will be, oh dear, 0.9 times 37.5, because it's 90% of that 37.5 stream that is ethanol. What's coming out? Well, 99% of M4 is ethanol coming out, and 1% of M5 is ethanol. So we have this equation. Is it solvable? No, too many unknowns. Okay, let's move on. Water. Okay, well, what's going in? Well, it's 10% of this 37.5 stream. And that is equal to, or what's coming out? Well, 1% of M4 and 99% of M5. Is it solvable now? Yes, same deal. It's just another simultaneous equations problem. So I'm going to do something similar to what I did earlier. I'm going to multiply this second equation. Let's label the equations up again, shall I? I'm going to multiply this second equation by 99. Okay, so 2 times 99 Let's just bung that in my calculator to see what I get on my left-hand side. So when I bung that in my calculator, I get 371.25. So that's just this times 99, if you didn't catch that. And when I multiply this by 99, that's just going to give me 0.99 M4. And when I multiply this by 99, that gives me 98.01 M5. Okay, and again, I can just subtract that first equation away. So when I subtract the first equation, on my left-hand side, that gives me 337.5. Now, when I subtract this from this, that gives me 0. Again, this is elimination, right? The M4 has been eliminated. And when I subtract 0.01 M5 from 98.01 M5, that just gives me 98 M5. Is that solvable? Yes, I just need to divide by 98. So I can say M5 is equal to 337.5 over 98, which is equal to 3.44. Now I've been a bit dumb here in that I've calculated M5 when I could have just calculated M4, but we can use the same logic that we did before, right? We can go back to our diagram. We can replace M5 with 3.44 kilograms per hour. Does that make sense? Well, most of this stream is water, right? And you can kind of see that most of the water left in this stream here. Most of the water left in this stream here. So it makes sense that that might be quite small, actually. And note that it's the second distillation column, right? So the feed will have been quite pure ethanol already, so there won't have been much water in the feed into the second distillation column anyway. So we can use the same logic that we did earlier. We can say that M4, which is what we're looking for, is equal to 37.5 feed stream minus 3.44, which is equal to 34.06. And that is our answer, okay? And that's what gives full marks. Just to kind of recap what we've done, we started off by carrying out a degrees of freedom analysis to see what was solvable and what wasn't. We discovered that the first column was solvable, so we carried out mass balances on our first column, which gave us these equations here, and then using simple elimination, we determined the values of our mass flow rates. And then having determined the distillate stream from the first column, which is then feeding into the second distillation column, that distillation column then becomes solvable, right? So we just do the same thing again. We carry out mass balances on our second column, which gives us these equations, and then again we just do a simple elimination, which gives us our answer. So the final part of this problem, and this is something that students oddly get stumped on, is determine the percentage proportion of ethanol from the feed stream that leaves in the distillate stream of the second column. Okay, so the percentage proportion of ethanol from the feed stream that leaves in the distillate column of the second, the distillate stream of the second column. So what do we mean by the percentage? First of all, we're talking about a percentage proportion. So we're asking, of this amount, how much, so of this amount, i.e. the ethanol that enters in the feed stream, how much leaves in the second distillate stream? You can probably tell this question is basically just asking, how efficient is our system? Of the ethanol that enters, how much of it leaves, right? So determine the percentage proportion of ethanol from the feed stream that leaves in the distillate stream of the second column. Well, the ethanol that enters in our first column is 40% of 100 kilos an hour, so that's 40. So we're asking, of that 40, how much leaves in the second distillate stream? Well, if we go to our mass flow block diagram, we can see that the ethanol leaving in the distillate stream of the second column is 99% of the overall mass flow rate. So we could write it out as this. We could say this is 99% of M4 over 40. But we know the value for M40. We just calculated it. It was 34.06 kilograms per hour. Okay. So let's just substitute that value in, 34.06 over 40. And when I type that into my calculator, I get 0.843. Note in the question, it's asking the percentage proportion. This is actually worth marks. So 0.843, what's that as a percentage? That's 84.3%. Okay. So that's the question. What I would recommend that you guys do to prepare yourselves if you're encountering something similar to this on an assessment is don't just follow along with this video. Have a go at solving the problem by yourself, and hopefully you might encounter some problems along the way, but maybe you can refer to this video or come ask me if you want to get over that hurdle. But otherwise, really have a go at kind of absorbing this all by yourselves. Right? Thanks for watching.